Hi everybody. This week we're going to work on bitmapped images. So a couple of projects to have a look at before we get into the code. Kyle McDonald's The Janus Machine is a really interesting project where he takes bitmaps actually of faces that are in 3 dimensions, so he's using a depth plane and manipulates those in 3D space. So have a look at that. And this is another interesting system for face tracking called Face OSC. There's a couple of videos there that explain how you can use face tracking to control systems and how you can also do face substitution with face tracking. Bitmapped images comes from chapter 9 of the textbook, so if you want to read along, that's where we need to be. So, images. To date, we've focused on vector-based images. We've been thinking of images as lines that are between 2 points in a space. So it's a Cartesian plane. We say an x and y position for the start of the line and another x and y position for the end of the line, and that's how we draw. We have curves as well. We have shapes made up of lines, but generally they're all vector-based. However, when we're dealing with things like photographs or videos, we don't draw a photograph line by line. We have a bitmap, a grid of values that have been measured from the environment with a lens and a camera. So it's a grid of picture elements or pixels. So a bitmapped image looks like this. We have a grid, and at the most simplest level we have simple on-off pixels, 0 and 1, and you can see there the values correspond to an image there, and we've drawn a line out of bits there. This is a more realistic type of situation where we have a photograph, and each pixel has a red, green and a blue value, 3 values that are mixed together, and they each have a location in X and Y for the grid as well. So the location's 81 pixels down and 81 pixels across and 123 pixels down. So that's red, green, blue, red, green, blue, red, green, blue. Here you can see that the green is 196 and the blue is 138 and the red is 137. So that's how you get that light green. The darker greens, much lower values overall, but still the same type of thing where the green is much greater than the other 2 colors. So processing's p-image class allows us to load images from JPEG files and from GIF files, and uses the image method to display them in the window. So this is a lot easier than any other way of loading images. So we just use the p-image class. We initialize something like a picture, and then we load an image from a file, and that file has to be in an easily locatable place. And then we use the image command to take that p image and put it in a particular location on the screen. 0, 0 is the top left corner for the top left corner. So let's have a look at that. Alright, here we go. So void setup, we set up the p image as a global variable by sticking it outside of the 2 methods. And then we have picture here, load image, fall.jpg, and we set the size of the screen with this surface.setSize command. The new version of processing doesn't allow you to set the size to a variable, so you have to set the size specifically and then change it. So we could add a size command there as well, but we'd still have to say surface.setSize to change it to this variable value picture.width, picture.height. And then here we have a little bit of code that gets the mouse X and mouse Y values and then sets the red, green and blue values appropriately. Sets the text based on that. So it's pretty straightforward when you see what's going on here. So wherever I look, you can see here we've got a very high blue value, red values. So the brown bit here, we've got higher red values than green and blue. Grass, green is the highest value. There we go. And down here for the grey, we've got pretty similar values across the board. Notice the alpha is always 255, that's fine. If we were looking at an image that had transparency in it, we might see something slightly different. Okay, so there we were using the get command to get a pixel value at a particular position in the screen. So color C equals get X value and Y value in the pixel buffer, and then we can look at the red value of C, the green value of C, the blue value of C, and the alpha value of C. So that was happening in that pixels example. So that allows us to look at each one of those bits in the map. The other thing we should note, of course, is we can also set these values, which will come later. Working with individual pixels gives us a lot of power and flexibility. We can do the same types of things that we can do with audio, where we work with individual sounds, with the values inside sounds. We can also do the same types of things with images. Images are two-dimensional, audio is one-dimensional, just time. But images are two-dimensional, so we can work both in the X and Y axis. And if we're looking at video, we can do three-dimensional as well. So let's have a look at some examples here. I'll have a look at pixelation first. So this is an image that we've broken up into pixels. We've dropped the resolution down quite a lot so you can see what pixels look like overall. And we can see this as a woman generally, but we can also see how each of the pixels have different values. So just to go into that a bit further, we can have a look at the same woman with different pixelation values and see what's going on there. Bit by bit, she becomes blurrier and blurrier and blurrier. Similarly, we can look at changing a picture into the negative. Here we have an image that we're loading called Principal, which is really just a photo. And you notice this looks like a negative version of the same. The sky, which is usually light in color, is dark, and the rest is light. So you can see here that we've set the colors to 255 minus the red value here. So the red value would normally be the color, but now we're doing the upside down version of that, 255 minus. So if I delete these 255s and hit that again, you can see the original image. So have a look at this one. Last one I'm going to look at is random neighbor. So random neighbor is here. And now we're actually going to interactively change the pixel buffer. And here you can see that we're doing some work with each of the values from the image. So you can see set x comma y, get new x, new y. So we're changing those values based on these lines here, a randomization process, and that's all happening within a y and an x loop. So we're moving across each of the spaces, the axes, I should say. So here you can see it's quite a kind of blurry effect that's going on. So if we change some of these values, let's see what happens. So that makes it twice as blurry. We're going wider. And that makes it even more blurry. So what's going on is we're getting values from around the general area of the actual pixel and replacing the pixel itself, x and y, with those values from nearby. So that's why it looks blurry, but it never actually continues to blur. We're always getting new values and putting them in different places.